Welcome to the Insightful Professor. In this video, we'll be concluding our lecture topic on type inheritance. We'll be presenting examples from the Oracle database. And as we do this, we'll be introducing two special operators, treat and is-of. These operators are used when dealing with substitutability with respect to subtypes and supertypes. After executing this statement, we can examine the structure of the Polygon supertype by using the +describe command. What is revealed is confirmation that it was declared as not final and also not instantiable. Specifying not final allows us to create subtypes. Specifying not instantiable says we'll never create an actual polygon object. The area method was declared, but it was not implemented in the supertype. We did not provide a type body. The reason we did not provide an implementation is because we expect that every subtype will override the method in a different way. Therefore, there's really no reason to define the method in the supertype. However, the way we defined it, a subtype could actually not declare an implementation. So a better way to approach this would be to define the member method as not instantiable. In addition to the type itself being not instantiable, we're saying that the member method is not instantiable. This is going to force each subtype to then override the method. If we attempt to create a subtype without specifying an override of the method, we'll get an error. Here we create circle, which is a subtype based upon Polygon. This subtype will inherit the area member function and must provide an implementation or definition of it. This is effectively an override of the function announced in the supertype. For that reason, we're using the keyword overriding to announce the member function of area. It also introduces its own local function called circumference. Again, after executing the command, we can use the describe command to find out information about this subtype. And the first thing we see is confirmation that this is an extension of Polygon. So we know that circle is a subtype. We also see the signature for the area method, which was overridden, and for the circumference method, which was declared locally. Also note the attributes. In addition to inheriting label from the Polygon supertype, we declared our own local variable of diameter that applies to instances of this subtype. We continue by creating the type body for circle. Note here that the word overriding, which appeared in the declaration of the specification for circle, must be included for the implementation when we're defining the area member function. So overriding must be used both in the create type and the create type body statement. That's a very important point. We create a second subtype of polygon called rectangle. A rectangle has length and width, and then also overrides the member function of area. Additionally, it includes its own local member function of perimeter. Executing the describe command subsequently reveals similar information to what we saw with the creation of the circle type. Remember that we did inherit label from the supertype, and then we've added length and width as local variables. The type body for rectangle, once again, note that we've included the word overriding when we declare the details of the area member function. Let's examine the metadata. For user types, we're looking at the name of the type the number of attributes, the number of methods, whether the type is declared as final, the name of the supertype, the number of local attributes, and the number of local methods. For Polygon, we see there's one attribute, one method. It's not final, obviously, because that is the supertype, and we declared subtypes based on that. But notice it has no supertype of its own, that's null, no local attributes, and no local methods. Those are both null. For circle and rectangle, we see that these were both declared as final. Remember, we did not explicitly say not final, so this is the end of the road. We can't declare subtypes of circle and subtypes of rectangle. Recall that final is the default. Both of these have a supertype of polygon, and then the information about local extensions. As we look at user type attributes, we see the attributes that are present in circle, the label and the diameter, and note that label is designated as being inherited from polygon, its supertype. Similarly, label is inherited for rectangle, and length and width would be the local attributes. Examining user type methods reveals that circle has area, and this is listed twice, and the same occurs in rectangle. Recall that area is defined in polygon, and it was inherited. The key here is that area has been overridden. We inherited it, but we also defined our own version of it by overriding it, both in circle and in rectangle, and that's reflected here in the output. Note that user type methods includes an additional column called instantiable. We did not include that here in our example. However, had we used that within the query, we would have seen that the area function in Polygon is not instantiable. We also would have seen that the inherited version of area in circle and rectangle also was not instantiable. We have now created our supertype, polygon, and two subtypes of polygon, circle and rectangle. A relational table that has a column of type polygon can hold either circle objects or rectangle objects. Recall that polygon is not instantiable, so we will never have any polygon objects. A relational table that has a column of type circle will be limited to holding only circle objects. And likewise, a relational table that has a column of type rectangle can hold only rectangle objects. Now we'll create tables to hold objects from this type hierarchy. We have a table called figures, which will hold polygon type objects. But remember, there will never be instances of polygon. So when we specify this will hold the supertype, we'll be able to insert any of the subtypes into this position. The circles table has a column that will hold only circle objects. The rectangles table has a column that will hold only rectangle objects. With the circles table created, we invoke the circle constructor and place a circle object into the figure column. Likewise, with the rectangles table in place, we invoke the rectangle constructor, placing a rectangle object into the figure column of this table. Note that there is a limitation here. Circles can only hold circle objects, rectangles can only hold rectangle objects, because these were both declared with the respective subtypes. So an attempt to insert into rectangles a circle object into the third column results in an error of inconsistent data types. With our two objects now created in their respective tables, we can invoke methods for these objects. So what we're going to do for circles is to invoke from the figure column the area method and the circumference method. For the figure column in the rectangles table, we'll be invoking the area method and the perimeter method. Recall that area was defined in the polygon supertype, and that both circle and rectangle provided an overriding of this method. It is these overridden methods that are being invoked here. Now comes the fun part. The figures table was defined with a type of polygon. That's the root type. This general type will allow us to place circle objects, a subtype of polygon, or rectangle objects, another subtype of polygon. We insert into figures, in our first statement, a rectangle object. In our second insert, we insert a circle object. And when we perform a query to retrieve this data, we see that we do indeed have a rectangle and a circle. This is an example of substitutability. A rectangle subtype is substituted for the polygon supertype, and similarly, a circle subtype. When dealing with subtypes stored in a general type, it is sometimes desirable to work with objects of a specified subtype. The treat operator is used to return only those objects that are of a specified subtype. Treat effectively changes the declared type of an expression. The example we present here retrieves all polygons stored in the figures table. For each object, its area is calculated, and if the object is a rectangle, its perimeter is returned. The perimeter is null for circle objects. The treat function does a runtime check to confirm that an expression can be operated on as if it were of a different specified type in the hierarchy. What this means is the treat function attempts to treat a supertype instance as a subtype instance. The supertype in this case is polygon. The subtype requested by treat is a rectangle. If the object that we're currently operating on is a rectangle object, then it makes sense to invoke the perimeter method, and that will be done. But if the object cannot be treated as a rectangle, if it's a circle, then treat returns null, and no perimeter method can be invoked. There are two main uses of treat. One is narrowing assignments, to modify the type of an expression so that the expression can be assigned to a variable of a more specialized type in the hierarchy. That is, to set a supertype value into a subtype. The other is to access attributes or methods of a subtype of the declared type of a row or column. A substitutable object table or column of type T has a hidden column for every attribute of every subtype of T. These hidden columns contain subtype attribute data, but you cannot list them with a describe statement. Treat enables you to access these columns. The isOfType operator or predicate tests object instances for the level of specialization of their type. For any object that is not of a specified subtype, or a subtype of a specified subtype, isOf returns false. Subtypes of a specified subtype are just more specialized versions of the specified subtype. If you want to exclude such subtypes, you can use the only keyword. With this keyword, isOf returns false for all types except the specified type. We include the syntax here, where expr would be the expression that we're trying to evaluate to see if this is of some particular type. The condition evaluates to null if this expression is null. However, if the expression is not null, the condition evaluates to true under either of the following circumstances. The most specific type of the expression is the subtype of one of the types specified in the type list, and only is not specified for the type. Alternatively, the most specific type of expression is explicitly specified in the type list. To use isOf requires the execute privilege on all types referenced by the type, and all types must belong to the same type family. It's also possible to test the type of the object that a ref points to. To do this, you would use the deref function to dereference the ref prior to testing with the isOf type predicate. This query is one that we've seen before, but now includes a where clause. Without the where clause, we actually returned two objects, one rectangle object and one circle object. Recall that the figures table, which is the target of this query, is declared as having polygon objects, which is a supertype of rectangle and circle. In this query, we're using the isOf in our predicate to ensure that the figure is a rectangle, and this eliminates circle from the result. This example uses a case expression to test the subtype and then allows us to invoke the treat operator accordingly. When the figure is a rectangle or is of the rectangle type, then we treat the figure as a rectangle and invoke the perimeter method. Remember that that method applies only to rectangles. When the figure is a circle or is of the circle type, we treat the figure as a circle and invoke circumference, the method that is unique to circle. And you see the result presented here. Substitutability applies to attributes, columns, and rows that have been declared to be of an object type, a ref to an object type, or a collection type. Attribute substitutability works as follows. An attribute defined as ref of some type can hold a ref to an instance of some type or to an instance of any subtype of this type. An attribute defined as some type can hold an instance of some type or to an instance of any subtype of this type. And finally, a collection of elements of type some type can hold instances of some type and instances of any subtype of this type. Object type columns and object type rows in object tables are substitutable. A column or row defined to be of some type T can contain instances of T or any of its subtypes. A newly created subtype can be stored in any substitutable tables and columns of its supertype, including tables and columns that existed prior to the subtype being created. A subtype can have an attribute that is a subtype. As an example, consider a student, a subtype of person, may have an academic advisor, another subtype of person. The columns of such types are not substitutable. You can turn off all substitutability on a column or attribute, including embedded attributes and nested collections, while creating a table. This is accomplished by using the clause "not substitutable" at all levels when you create a table. This turns off all column or attribute substitutability, including embedded attributes and collections nested to any level. The following examples serve only to illustrate syntax. The first example demonstrates the "not substitutable at all levels" clause on a column. The second example demonstrates the clause being applied to an object table. The is-of type constraint allows you to impose a constraint that limits the range of subtypes permitted in an object column or attributes to a particular subtype. We discussed the use of the only keyword previously. Here's an example showing how it could be used. So we see that is-of can only be used to constrain a single subtype. Only must be specified. Also note that either is-of or not substitutable at all levels can be used to constrain column objects, but you're not permitted to use both. This concludes our lecture on type inheritance. This final segment has provided several examples of how these features have been implemented and how they're supported by Oracle Database. If you have any questions or comments, let us know and we'll try to get back to you as quickly as possible. And once again, thanks for watching.